Okay, it's Brian, and this week we're doing circuits, but we're doing circuits part 2. And we're going to add a couple of things to the mix. First off, we're going to look at more complex circuits, and we're going to look at a resistance model of the human body. And so we're going to talk about safety. We're going to add capacitors to the mix and talk about capacitor circuits that allows for timing. And then finally, we're going to talk about electricity in the body, and we're going to look at signal conduction in neurons. Very, very fun stuff. And let's look at the key principles we're going to look at this week, or the key relationships. One is if I have resistors connected in series, so one after another, like so, the total resistance is just the sum of the individual resistors if they're connected in parallel. So they're hooked together at one side, hooked together at the other, and so there's the same potential difference across each one of them. The equivalent resistance is given by this relationship right here. It's 1 over the sum of the inverse resistances, and you'll have some chance to do that. And then for RC circuits, or circuits consisting of a resistor and a capacitor connected together, we're going to look at the voltage across the capacitor. So if I take a capacitor and hook it up to a resistor in a circuit, and I close the switch so that current can flow, as current flows, the capacitor will discharge, so the voltage will steadily decrease, as in this graph right here. And we have a relationship to describe the decrease in the voltage, and it looks like this. The voltage is equal to its initial value times e to the minus t over RC. Well, RC is the product of the resistance and the capacitance. That's the time constant for the decay. It's kind of a characteristic time, and we'll see some examples of this. Finally, when we look at resistance, and when we look at electricity going through the body, and we're going to consider that when we're talking about electrical safety, we have a resistance model of the body that looks like this, and we'll talk about how that works in a little bit. Now, last week we talked about Kirchhoffs Voltage Law and Kirchhoffs Current Law, and we're going to start the week with a couple of things that test our understanding of that. Here's the first one. The question asks, in this circuit, what is the voltage across the 20 ohm resistor? Well, if I know the current that flows through this resistor, I can calculate the voltage across it, because the voltage across the resistor is just equal to the current times the resistance. I know the resistance, and I can figure out the current by looking at this. 2.5 amps through this resistor, 1.5 amps through here. Using Kirchhoffs current law, or just conservation of current, I can figure out how much current goes through the 20 ohm resistor, and if I know that, I can calculate the voltage. We'll do that one in class. And this problem asks us to consider Kirchhoffs voltage law, basically, or just if I go around a circuit and I end up where I started, I better end up at the same voltage. And the question asks, what is the voltage across the 200 ohm resistor? Well, to do that, we're going to say, let's look at the voltages, or the potential at different points in the circuit. We always take the bottom left as 0. And then right here, I've gone through a 4.5 volt battery, and I've gone towards the positive terminal, so I've increased in potential. So this is going to be 4.5 volts right here. And you can just work your way around the circuit and look at the potentials at different points. And if you do that, you can come up with the potential difference across that 200 ohm resistor. One thing you have to know is the direction of the current through the resistors. And in fact, we know the current goes this way, looking at the potential differences across these batteries or power supplies here. They're definitely going to drive current in a clockwise sense. And so for each of the resistors, the positive end of the resistor is where the current comes in. It goes downhill basically in the resistors, and so the other end will be lower. With that in hand, you can look at the potential at different points in the circuit, and therefore you can calculate the potential difference across the resistor. We will do that one in class, but you have everything you need to be able to solve that right now. Next piece we want to talk about is a resistance model of the body, and we're going to do this when we consider electrical safety. So rather than looking at just kind of like random resistor circuits, we're going to say, no, let's do something really practical. Suppose you touched something at a high voltage with one hand, so say 1,000 volts, and the other hand you touched something that was at 0 volts, so something that was grounded. Well, there's going to be a potential difference across your torso. We can calculate how much current flows, and look what's going to happen. Current is going to go through your skin, through your arm, through your torso, through your arm, through your skin, and over to 0 volts. And so I've got a conducting path through the body, and if I was to redraw it, it looks like this. I got 1,000 volts here. I have the resistance of the skin, the resistance of the arm, the resistance of the torso, the resistance of the other arm, the resistance of the skin, and then over at 0 volts. And these resistors are all in series, and so I can calculate the total resistance of the current path. And if I know that and I know the potential difference, I can calculate a current. So basically, you're going to draw a conducting path through the body. You're going to represent it as a series of resistors, calculate an equivalent resistance, and we can use that to calculate the current. And as we know, it's the current that you have to worry about. High voltage by itself isn't dangerous. What's dangerous is current. And let's take a look at a problem that works like this. So suppose someone is changing a light bulb, and she's doing this in a chandelier, and I'll show a picture of this in class. And this person, with one hand, touches a grounded metal frame of the lamp, so it's at 0 volts, and the other hand touches a hot inside terminal. Well, hot terminal is going to be at 120 volts, okay? There's going to be a current that goes through her body, and it's going to go through the skin, through the arm, through the torso, through the arm, and through the skin, like so. And we're told to assume that the resistance of the skin is 4,000 ohms, and that's going to be true on both hands. Okay, we can calculate the complete resistance of the current path, and it's going to be 4,000 plus 310 plus 30 for the torso plus 310 for the other arm plus 4,000 for the skin. And I can compute the total resistance. I can also compute, or I also know the voltage, the potential difference across the person's body is 120 volts. So the current is just equal to delta V divided by R. Delta V is 120 volts, and the resistance is just the total resistance, or the effective resistance. I can calculate a current. That's the kind of problem we're going to take a look at in class. And now we're also going to consider this case. So you're in the tub with your lower body well grounded. Well, if that's the case, okay, let's take a look at this. Lower body is well grounded. So basically, the torso ends up, the bottom of the torso ends up at 0 volts. And then you touch a poorly wired appliance with a hot case. So what that means is the hand here is at 0 volts. The lower end of the torso, the hand is at 120 volts. The lower end of the torso is at 0 volts. And the path through the body is basically skin, arm, torso, and then to ground. And so it's just it's a shorter conducting path. And also, since you're in the tub, the skin resistance is a lot lower. Question, are you okay? And I think you know the answer to this. This is a very dangerous situation. This is, in fact, a worst case scenario. We can compute the equivalent resistance of the conducting path, just the total resistance. It's a series resistance of the skin plus the arm plus the torso. And we can compute that value, and then the current that flows is just equal to the potential difference across that resistance divided by their total resistance, and you end up with a current which is in fact pretty scary, and that's something we'll calculate in class. Okay, next up we're going to look at a capacitor circuit. Okay, so a capacitor discharging through a resistor, and the circuit basically looks like this. I got a capacitor, I have a switch, I have a resistor, like so. And as soon as the switch is closed, whoop, like so, then a current flows in the circuit, the capacitor discharges, the voltage across the capacitor decreases as a function of time. And here's a graph that shows the voltage across the capacitor as a function of time, and we've marked a couple of special times, tau and 2 tau and 3 tau. Tau is the time constant. It's the product of the resistance times the capacitance. And it's sort of a characteristic time for the decay. In a time of tau, the value decays from its original value to 37%, or 1 over e of its original value. So tau is kind of a 1 over e life. And it's kind of like a half-life. If you want to use the actual half-life, it's just equal to tau times natural log of 2, okay? And we have a relationship for the voltage across the capacitor as a function of time, and it looks like this. And we can use that for more complex calculations. So we'll either use this equation, or sometimes we're just interested in what is the characteristic time for the decay. And by the way, too, there's a similar equation for the charging of a circuit, of a capacitor circuit, and has a similar characteristic time. Now, the first problem we'll look at is a defibrillator. And a defibrillator just has a big capacitor charged up to a really high voltage that you connect across a patient's torso. And you do that with conducting gel on the plates so that the effective resistance is very, very low. So for this case, defibrillator connected to a patient's torso. What is the current the instant the switch is closed, and what is the current 5 milliseconds after the switch is closed? I'm going to first prepare by drawing a circuit, and it's a capacitor charged up, connected to a switch, connected to a resistor. Okay, and then when I close the switch, current flows in the circuit, and the voltage decreases as a function of time, as we have seen that it will. Okay, so the voltage decreases as a function of time. Another thing we're going to do to start is we're going to compute the time constant. Okay, now the time constant for this discharge is just equal to the product of the resistance times the capacitance. Okay? And so we're going to go ahead and compute that. And if we do that, it's 3.2 milliseconds. It's a product of 32 microfarads, or 32 times 10 to the negative sixth, and then times 100. So I end up with 3.2 milliseconds. And the product of resistance in ohms times capacitors in farads is in fact seconds, which you can verify. So the 5 milliseconds is a bit more than one time constant after the switch is closed. Okay? So what we're going to do, the way we're going to solve this problem is as follows. We're going to look at that circuit, and I've got a certain voltage across the capacitor, which we call delta VC, and that changes with time. And then I'm going to look at the current in the circuit, and I know that the current is just equal to the voltage across the capacitor divided by the resistance. Now, at time t is equal to 0, the voltage is 5,000 volts. That's what it is when you close the switch. And the resistance is 100 ohms. So the initial current is going to be 50 amps. So it's a huge current. And we can compute it at that later time by going as follows. The voltage across the capacitor is equal to its initial value, which is 5,000 volts, times e to the minus t over tau. Now t is the time. That's the 5 milliseconds. So that goes in for t. Tau is equal to the time constant, so that goes here. And I can compute the voltage across the capacitor. With the voltage across the capacitor, I can compute the current using this relationship right here, which we used previously. And since it's a bit more than one time constant, I know it's going to be a little less than 37%. And that is in fact a problem we'll take a look at in class. Now, the next thing we're going to do is we're going to talk about electrical signals in the nervous system. And this is fascinating. We're going to start with just a quick calculation. So if you take a typical cell membrane, and it's also the typical thickness of the membrane of an axon, it's very, very thin, 7 nanometers. And the potential difference across it is something like 70 millivolts, as we talked about previously. So the electric field, and the electric field is just equal to the difference in potential divided by the distance over which that potential changes, is in fact going to be very, very large, because delta D is very small indeed. And it comes out to be about 10 to the 7th volts per meter. So the electric field inside the cell membrane is very, very large indeed. We are electric organisms. That is 10 times as large an electric field as you need to throw sparks. And now let's look at signal conduction in an axon. So here I have a really, really simple model of a nerve cell. It's basically a cell body with a little axon sticking out of it. And if I trigger an action potential right here, okay, and I can do that by changing the potential on the cell membrane a little bit. You trigger an action potential, ion channels open, and in the inside of the cell changes from being negative to being positive, okay? That's the action potential. And when that happens, it triggers the adjacent part of the cell membrane. Basically, if you change the potential of the cell membrane a little bit, you open up the ion channels. They are so-called voltage gated. So if you trigger this ion channel, you trigger the next one, which triggers the next one, which triggers the next one. And I get this wave of action potential that makes its way down the axon. Okay? And that is how a signal will propagate in an uninsulated axon. Now, we're going to analyze this using physics because this is a classic physics problem right here. Now let's talk about how you would do this. So suppose I have a segment of an axon here, and down here, an action potential has been triggered. So it's positive inside, and down here it hasn't. And so it's negative on the inside. Well, there's a potential difference across this fluid inside the axon, and it is going to drive a current down the axon, and charges will move. And when the charges move, they're going to change the potential inside the cell membrane, and when it gets to be positive down here, ooh, that's going to trigger an action potential there, and so the signal will continue. Now, how long is it going to take to transport enough charges down the cell membrane to change the potential at this end? That depends upon a couple of things, and one thing it depends upon is the resistance of the fluid inside the axon, okay, because the charges are flowing down the salty fluid inside the axon. The cell membrane itself is actually a pretty good insulator, but the fluid inside is not, and you calculated a typical resistance for the fluid inside an axon a while ago, but we're going to try to do that again. And the way you calculate it is you just say, like, look, the resistance is equal to the resistivity times the length divided by the cross-section area. We know that. We know that's how it's going to work. And I know the resistivity, okay, we're told that, and that's a typical value, okay. And I'm told the radius of the axon, and I'm told the length, okay. And with all those things in hand, I can calculate the resistance, and we're going to come out with a pretty big resistance. It's going to be on the order of 25 mega ohms. And what that means is, with a high resistance and a small potential difference, charges are not going to move very quickly. The current will be small, and that is going to lead to slow signal propagation. How slow? There's one more piece we have to calculate. All right, next piece of the puzzle is look at the capacitance of the axon. So consider this. Charges are moving down the cell membrane. And to be able to trigger an action potential further down the cell membrane, I have to charge it up. Remember, it starts out negative on the inside, positive on the outside. I've got to change that potential. And to do that, I have to move charges. So I basically have to charge up the cell membrane. And I'm charging up the cell membrane with charges that I am moving down the center of the axon, which has a certain resistance associated with it. And when I've moved enough charges to change the potential across the cell membrane, that triggers an action potential, and the signal will continue. So basically, I am charging up the capacitance of the cell membrane. And what is the capacitance of the cell membrane? Well, suppose I split it right here, and I roll it out flat. And so the inside is now here, and the outside is underneath. And in between, there's a layer of cell membrane. And the area of that is just the circumference of the axon times the length, okay? That is the area of the capacitor, because I just rolled that thing flat because I'm charging up basically the cell membrane. It's got salty fluids on the inside, salty fluids on the outside, with an insulator in between. It's a capacitor. And we're going to calculate a typical capacitance for this length of axon. It's 1 millimeter long. It's got this radius. I know the dielectric constant of cell membranes, and I know a typical thickness. With all those things in hand, I can calculate the capacitance, because the capacitance is the dielectric constant times epsilon 0 times A divided by D. I can calculate all those things. And with all that in hand, I can calculate a capacitance. And with the resistance and the capacitance in hand, I can calculate a signal speed, because we're modeling it this way. I trigger an action potential, okay? That's basically like turning on a power supply or closing a switch on a circuit, and then current is going to flow in a circuit, and it's flowing through a resistor, and it's charging up a capacitor. How long is it going to take to charge? Well, we're just going to say it's going to charge up enough in a time of one time constant. And so the characteristic time for the RC circuit, just the product of R times C, we're going to approximate that's how much time it takes to charge up the cell membrane. And that's an approximation, but it turns out it's a pretty decent approximation. How fast will the action potential propagate from one end to the other? Well, speed is just distance divided by time. So it's just the length of the axon divided by the time constant. And when we calculate that, we're going to end up with a really, really slow transmission speed. So how do we make it faster? Suppose I double the radius of the axon. Okay? If I double the radius of the axon, how does that affect the resistance? Well, if I've doubled the radius, the area, which is pi r squared, goes up by a factor of 4, so the resistance goes down by a factor of 4. The capacitance is going to go up because I'm going to take the area, and remember we said the area was 2 pi r times L. That's going to go up by a factor of 2, and the capacitance is kappa times epsilon 0 times A divided by D. D doesn't change. That's the thickness of the cell membrane. Capacitance goes up by a factor of 2. Net result, tau, which is equal to R times C, is going to go down by a factor of 2, which means the signal speed is going to go up by a factor of 2. Oh, so if I make the axon twice as big, it conducts a signal twice as fast. I've increased the capacitance, but I've dramatically decreased the resistance. Net result, I get a faster charging of the cell membrane, faster signal speed. The problem is, that's not a, you have to make the axon really, really large to get a reasonable signal speed. In fact, that happens in squid, but in you, that would be tricky to fit all the axons that you need into your body. So the other strategy you can use is this. Take an axon and wrap it in a myelin sheath. And if you do that, you're not changing the cross-section area inside. So how does it affect the resistance? It doesn't. No change. How does it affect the capacitance? Well, the capacitance is equal to kappa times epsilon 0 times A divided by D. The area doesn't change, but D goes way up. So the capacitance goes way down. Okay? So the net result is I'm going to take my time constant, R times C. It's going to go way down. And so the signal speed, which is L divided by tau, is going to go way up. So the myelin sheath will increase your signal speed, but not only will it increase the signal speed, what it will also do is increase efficiency. Because, think about this, when you're charging up a cell membrane, you are charging up a capacitor. And we know the energy stored in a capacitor is equal to 1/2 times C times delta V squared. And delta V is the potential of the cell membrane. So if the capacitance goes down, the energy stored in the capacitor goes down as well. And this is not trivial. And so to have reasonably fast nerve conduction and to have reasonably efficient nerve conduction, you got to myelinate the axons. And that's a very, very adaptive thing. And we are put together that way, which is a good thing. So that's where we're going to finish. So this week, not quite as much new material because we're going to have an exam on Friday. I'll see you folks in class.